Ladies and gentlemen, welcome to the Royal Society 2010 Bakerian Prize Lecture. My name is John Pethiker. I'm the Physical Sciences Secretary and Vice President of the Royal Society. Could I start with just a few mundane items like please turn off all your cell phones for real, or put them into some mode where they don't make any kind of noise. And one of the many reasons for that is that this lecture is being webcast and recorded, so it would be very helpful if you could ensure that really extraneous noises don't come into that process. Thank you very much. Well, this is the Royal Society's 350th anniversary year, and there are numerous events going on throughout the year, Hawksby Awards and many things which you will see on the Society's website and other locations. But in fact, our lecture tonight stems from a considerably earlier period, and I have here a few notes about this. So the Bakerian lecture is the Society's premier lecture in the physical sciences. It originated in 1775 through a bequest by Mr. Henry Baker, Fellow of the Society, for £100 for an oration or discourse which was to be spoken or read yearly by one of the Fellows on such part of natural history or experimental philosophy at such time and in such manner as the President of the Council may at time order and appoint. So that's the origins of it in 1775. Well, our speaker today for this premier prize lecture of the Society is Professor Donal Bradley. Donal Bradley, a brief summary, is a graduate of Imperial College and did his doctorate at Cambridge University, doing that in 1987. He returned to his alma mater, Imperial College, in 2000 as a professor of experimental solid-state physics. He became a Fellow of the Royal Society in 2004, head of department in 2005, and became the Lee Lucas Professor at Imperial in 2006. And he has various other roles in Imperial College as well, including first director of the newly established Centre for Plastic Electronics, which is one of the key national centres for excellence in this area. He was awarded the CBE in the 2010 New Year's Honours List for services to science. He is, of course, one of the world's most highly noted physicists, being amongst, I see here, the 1% of the most highly cited physicists in the world. But not only that, he's been involved in commercialization as well, and is co-founder of Cambridge Display Technology, co-founder and director of Molecular Vision Limited, member of Sea Change UK LLP, and director of Solar Press Limited, and no doubt many more, with more than 20 patent families to his name. So a brilliant and glittering career. Ladies and gentlemen, I'm very pleased to present Professor Donal Bradley.
So good evening, ladies and gentlemen. It really is a great pleasure to be here this evening to give this Bakerian lecture. The title of my talk is Plastic Electronics, the Science and Application of Molecular Electronic Materials and Devices. And what I'd like to do is to explain what plastic electronics is and how we can think about using plastic electronic materials to make quite a wide range of interesting devices. On a personal note, I would also like to dedicate this lecture to the memory of my father, who sadly died earlier this year. He was also a Fellow of the Royal Society and a pioneer of laser science. And I will actually be able to refer within my own lecture to some areas that he was working on, which overlap, in fact, with some of the things that I have also been able to work on. I also felt that it was very important to point out right at the start that this sort of work involves a very large number of people in terms of collaboration. It's a field where it's essential to bring together people from a wide range of different disciplines, so from chemistry, material science, physics, engineering, if you really want to make things happen. And I have a list here, a partial list I should emphasize, of people who have been working in this field and who it's been my pleasure to be able to collaborate with over many years, initially in Cambridge, then in Sheffield, and now at Imperial College. So talk outline is as follows. I'd like to spend a little bit of time introducing plastic electronic materials, tell you about their basic properties and their potential for applications. I'll say a little bit about our first, if you like, foray into commercial area where we were involved in a discovery that led to the opportunity to make light-emitting displays using these kinds of materials. I'll then say a little bit about some other areas that we're now looking at where there are good opportunities also to think about opportunity for commercial applications. And then finally, I'll say a few words about some of the nitty-gritty of the kind of research that we're involved in, and particularly looking at ways in which we can use the molecular nature of these materials to allow us to control properties to give rise to interesting opportunities. Now, breaking with tradition, I suspect, I borrowed a theme from Have I Got News for You? And the theme is, what's the link? And so I've put here a number of items and objects, people. So we have Robinson Crusoe, we have Simon & Garfunkel CD, we have Phil Collins, Tony Banks, and Mike Rutherford, we have a James Bond DVD, and we have a photograph of a motley rugby crew from Wimbledon College. So the question that I'd like you to kind of bear in your mind as we go through the talk is, what is the link between these objects? And I'll help you as we go through, but I thought it would be interesting to do that. So starter for 10, as it were, is that Robinson Crusoe was written by Daniel Defoe, whose daughter Sophia married Henry Baker. And Henry Baker, of course, was the benefactor of the lecture that is being presented tonight. So that gives you an idea, perhaps, of the obvious connectivity between what I'm presenting here. It does get better, I have to say. So the second one is Simon & Garfunkel. Now, one of the songs on that Simon & Garfunkel CD is Mrs. Robinson. Okay, so we're getting an idea of how my connections work. So what's the connection between Mrs. Robinson and the subject of my talk? Well, it is just one word, plastics. Now, just one word, plastics, is actually a quotation from a film, and that film is The Graduate, 1967. According to the American Film Institute, it's actually the 42nd most memorable film quotation. Okay, so now you know, plastics, as a single word, is the 42nd most memorable film quotation. And if you remember the film, or if you want to look at the film yourself, look out for a scene where the hero, Benjamin Braddock, who is a graduate, hence the title of the film, is thinking about his career. He's thinking about what he should do now that he has graduated, what should he go into, and he's looking for advice. And he gets all sorts of advice, most of which he doesn't actually want. And one of the people giving him advice that he doesn't actually want is a certain Mr. Maguire. And Mr. Maguire says, in answer to the request or not for advice, just one word, plastics. Now, at the time this film was made, that actually caused the film audience to fall around in laughter. And you could say, well, why? What was so funny about that? And the whole point was that at that time, plastics were seen as deadly boring, basically imitative, unnatural, things that a dynamic graduate simply would not want to work on. And that's, if you like, where we start, and I hope where we finish up with is that if I say to a young graduate just one word, plastics, you will think, oh, that's really exciting, hopefully, and won't have the same response as was had at this time. So what are plastics? Well, plastics, also known as polymers, also known as long-chain molecules. How can we demonstrate a long-chain molecule? Well, the simplest idea I had was to get a pile of paper clips and link them all together to make a chain. So here is one unit in that polymer chain. We've made a polymer by stringing a whole series of units together. So this is my polymer chain. We'll come back to some things about polymer chains a bit later on. But really, why have plastics become so important? They've become very important because they make very good structural materials. They're lightweight. They can be very easily manufactured into objects. So here's another object, which we'll come back to a bit later. It's a plastic fan. It's a bit more than a plastic fan, so we'll come back to that in a little while. They are basically cheap. They're brightly colored. They have good insulating properties if you're thinking about using them in terms of electricity. And they can have also very good optical properties. So they have lots of things that are desirable, so in terms of their functionality, and they can be processed. They can be very easily processed into the shapes, objects. They can be colored. They can have all of those sorts of properties. And here is a selection of plastic objects from our kitchen at home. You, I'm sure, would be able to think of many others that you could choose. But you can see these are brightly colored, they're cheap, they're cheerful, and jolly useful. So that's what plastics are. Now, what if you could take all of those things about plastics and add to them? And the adding to them perhaps might allow us to give those plastics the conduction properties of a metal, or they might allow us to have the controllable properties that we think of in terms of semiconductors, so light emission, absorption, electronic device formation, and so on, that we have in traditional semiconductors. So what if we could add those functional properties to the properties that we've been talking about? What if we could add the absorption and emission of dyes that, for instance, would be used to color a display screen or for making a laser or an amplifier? What if we could add all of those things to the basic properties of a plastic? Well, that basically is what we're trying to do, and that is the exciting possibility that we have for a particular type of plastic or a particular type of polymer, and those polymers we call conjugated polymers, and I'll say in a minute what a conjugated polymer is. But in a conjugated polymer, we have the opportunity for the electrons within that system to delocalize and move around, as they do in a metal or a semiconductor, in a way that is different to traditional plastics, where, in fact, the electrons essentially are strongly localized into bonds between atoms, and so they have insulating properties. So what are conjugated polymers? Well, conjugated polymers are a particular class, and essentially they are characterized by having, if we draw the chemical structures, by having an alternating sequence of single and double bonds along the chain. So if we look at a benzene ring, for instance, we can draw this as a delocalized pi system. We could also put in double bonds into this ring, and we would see that there's an alternation. It goes single, double, single, double. And that tells us that the electron bonding, we essentially have a carbon atom with 3 sp2 hybrid bonds, and we have this one orbital, a pz orbital, which sticks out of that plane, and it's the overlap of these pz orbitals that gives rise to a double bond, or if we think of it along the polymer chain, gives rise to this delocalized electronic structure. Now, this is just an example of one family of materials, and we'll come back to these. These are called polyfluorines. So this is probably quite a good place to start if you're thinking about materials that are fluorescent, because the name is fluorine, so a highly fluorescent conjugated molecule is what actually that name means. So it's quite a useful family to work with. What we can see here is a range of fluorescent molecules from this family, where we basically have the materials dispersed in a solution. We can see that we basically get emission across the full visible spectrum from blue all the way to red. And we can essentially use chemistry to tune the optical gaps, and we end up with, if you like, a system of materials that we can describe at a simple level as being either medium to wide gap semiconductors. So that's what we're working with. But it's not just medium to wide gap semiconductors that we're working with. We're working with molecular semiconductors, and that word molecular is very important in understanding the attributes of these materials. And in a molecule, the interactions that take place within the solid between two molecules are typically van der Waals forces, and those forces are much weaker than the covalent bonds that exist in a single chain. So going back to our polymer chain, these are all nicely linked together. If we put another chain next to it, they basically are not linked together hardly at all. And we can basically move them apart, we can basically move them around, we can do things with them in a way that allows us to basically process the materials to make the kinds of things that we want to make. So those weak van der Waals forces can be acted upon by a solvent or by heating the material, so we can make a solution, we can make a melt. And in that solution or melt, we can then reconfigure the shape of the object that we want. We can reconfigure the state in which that object exists. And we can make a whole series of materials. We can make films, which we use in our devices. These can be just a single component. We can basically mix things together. We can blend things together. We can do a lot of mixing and matching and arranging that we have the properties that we want in our samples. And we end up with a very rich interplay between the local environment, the physical structure, and the desired mechanical, thermal, optical, and electrical properties. And that rich environment basically is one of the big attractions to working with this sort of semiconductor. We really have a lot of opportunities to do things that we can't very easily do with conventional semiconductors. And just one example, for a particular polyfluorine, this polydioxyl fluorine, a blue polyfluorine, is we can make a solution of the material where the polymer chains are nicely separated and dissolved up in the solvent. So that's here. We've got a solution. We can basically change the nature of that solvent that we use to dissolve the material, and we can use a less good solvent. And in the presence of this less good solvent, we end up with something which is called a gel. And so here's our gel. And basically, the gel is now a solid, and it doesn't fall down when you turn it over. The solution basically moves like a fluid. The gel basically stays put. And that's just a physical change. And the physical change is associated with formation of a particular conformation within the polymer chain. And these conformational defects or conformational units interact strongly with each other, and they gel the solution. We end up with this gel. And if you look at the optical properties, here's the normal solution under fluorescent excitation. We get a nice blue color. In the gel, we see a sort of turquoisey green color, and we'll come back to that later in the talk. But this is characteristic of having the presence of these altered conformations, and these altered conformations have a different optical gap and therefore emit with a different wavelength. Now, this is a hard slide, so we're going to try and go through this one slowly. So what are the key electronic structure features that differentiate this kind of semiconductor from conventional semiconductors? So there's lots of science words on here. So molecules have localized wave functions. They're not rigid band semiconductors with block wave states. What do I mean by that? Well, it's actually very hard to explain in words of one syllable what I mean by that. And so I thought of one way to try and explain what I mean by that. And that is, if you imagine basically a solid block of granite and next to it a rubber sheet, okay? And if you put an electron onto your solid block of granite, it essentially spreads out, and you basically don't really see that it's there. You know it's there. You can do a measurement on it. You can find it somewhere when you do that measurement, but it's just spread out on that solid surface. And that would be a conventional inorganic solid semiconductor with block wave functions. Now, my rubber sheet is my molecular semiconductor. And basically, when I drop my electron onto it, think of a marble, then basically locally, where I drop that marble, the rubber sheet actually distorts. And we will see a dip in the rubber sheet, and that is a localization of that state, that electronic state, on that rubber sheet. And it's because the rubber sheet basically can adjust to the presence of the electron. It can alter its geometry in the presence of that electron. So that's my analogy. It's not a very good one, but hopefully it will give you some idea of what we're thinking about. And there are many consequences that follow from that localization. Firstly, we have very strong absorption coefficients. What does that mean? It means that the materials we work with are very strongly colored. So a thin film of these materials absorbs a lot of light and has a bright color. So we don't need a large amount of material to absorb the light. And typically, the absorption coefficient is about 10 to the 5 per centimeter, which compares to about 10 to the 3 per centimeter for something like silicon. We also have this coupling of electronic and local vibrational degrees of freedom. So again, thinking of my rubber sheet, if I drop my marble onto it, it basically will oscillate a little bit. And that oscillation you can think of as a coupling between that electronic state and local vibrational modes of the material. So there's this oscillation. And that oscillation means that the excited state is actually coupled to vibrational states, and those vibrational states will then appear spectroscopically, so we'll see some features of those vibrational states. We'll see a series of lines that we call vibronic structure. It also means that if we want to move our electron around, we can't actually move it around as we would the marble on a nice piece of granite, where we can just zip it about. It can move freely around. Basically, we have to give it a tap, and it has to somehow jump out of the well, and it then drops into another space on the rubber sheet and sinks in again, and we have to knock it back up again. And so, if you like, there's this hopping motion of the charge as it moves across that rubber sheet. And a consequence of that is clearly that it's harder to move that charge around, and so it actually moves more slowly if we want to move it across our material. We also have a strong interaction between the electrons in our systems, and because of what we call a small dielectric constant, there is weak screening of that interaction. Now, that's quite a hard thing to explain. Basically, the electron, because it's localized, experiences the charge of another electron or an absence of an electron in a hole quite strongly. So they see each other quite strongly. Whereas in an inorganic semiconductor, conventional inorganic semiconductor, because those charges are much more spread out, the interaction between the two charges is much weaker. And we end up with states which are strongly bound. So this electron and hole are strongly joined together. They're held together by a large Coulomb binding energy, which is about 0.2 to 0.5 electron volts. And we get other things from quantum mechanics. The fact that these states are described in terms of fermions means that we have triplet states. And probably not too much to say about that without sort of going too far. So we can say that these are the key electronic structure features. They give rise to this large oscillator strength, so strongly absorbing, strongly emitting materials. The coupling to the local vibrations gives us a large bandwidth, which means that they emit over a large wavelength range. The mobility is typically low compared to conventional inorganic semiconductors. The fact that we have these strongly bound states means that they tend to emit light rather than separate into charges. And so that tendency to emit light is very good if we want to make a light source. It's not so good if we want to make a solar cell where we actually want to generate charges in an external circuit. And then in terms of these triplet states, there are other things that go on in terms of photochemistry and so on. And we'll kind of leave that to one side for now. What are the other key features? Well, clearly an object like this is anisotropic, so it's long and thin. It basically is an anisotropic object. And that anisotropy is intrinsic to the nature of the material. And in the appropriate circumstances, we can actually generate something which shows highly anisotropic properties. And so instead of having a nice pile like this of polymer chains, if we very carefully take them out and basically align them all up nicely, we end up with a highly anisotropic object. We can do that in a number of ways. One is to make use of what's called a liquid crystalline phase for the materials, and we can arrange that they line up like this. And when they line up like this, they are very anisotropic. And so, for instance, we can see, if we look at their optical properties, they have a very strong polarization of the absorption and the emission. We can use that to make interesting objects, so polarized light sources. We also see that if we want to look at charge transport in these materials, it's much easier for a charge to move along that chain than neighboring chains. So if we make it anisotropic, we see quite strongly anisotropic transport. Now, another feature is that typically these materials are disordered. And here's our disordered material, just a nice pile on the table. And that disorder gives rise to a broadening of many of the optical features. It gives rise to, again, effects in terms of transport. And perhaps the easiest way to think of that, using our rubber sheet analogy, is that we have a rubber sheet that's become a little bit worn in some places and a little bit thicker in other places. And therefore, the amount by which we get a distortion of that rubber sheet varies across the surface. And so basically, there is a distribution of energies within that system if we're moving the charge around. Sometimes it will sink in more, sometimes it will sink in less. And we see that when we look at the transport through these materials. Now, this slide is a very busy slide. This slide is actually a calculation, Mike Winokur and colleagues, and it basically shows the conformational energy of the same polymer chain that we were talking about, this dioctyl fluorine polymer chain. And what's plotted is a torsion angle between units of the polymer chain, so the angle by which two units twist relative to each other. So it's plotting that angle and plotting the relative, this is mechanical energy, kilojoules per mole per monomer. And you see all sorts of data points on here. And these are all different conformations of the polymer chain. And so if we have a long polymer chain, we can do all sorts of things with it. We can basically put it into a conformation where it's like this. Here's another conformation. It's fully extended. And there are all sorts of conformations in between. And this is a calculation of what some of those conformations look like. Now, the conformation that gave rise to the gelation is actually this point. And it's a rather isolated point. And that isolated point is very interesting because it's a well-defined point, and again, we'll come back to look at some of the properties of that point later. And basically, that point corresponds to a very particular arrangement of the side chains so that they basically fold up and lie nice and neatly along that polymer backbone. And that extended conformation is this so-called beta phase conformation. And as I say, we'll come back to some of the interesting properties of that a little bit later on. So if we want to summarize up to this point, what are the things that we've been thinking about? We've been thinking about basic properties, so attributes of these materials, localized wave function, low dielectric constant, disordered anisotropic, giving rise to large efficiency for photoluminescence, absorption coefficients. So these are the attributes of our materials, and then these are the sorts of applications that we have in mind. And essentially what we have to do as researchers working in this field is to think about these attributes and how they might allow us to apply, to be able to do these sorts of applications. And different attributes will be beneficial for different sorts of applications, or we may have to worry about some of these attributes if we're thinking about particular applications. And so we're thinking about how to connect those basic properties of the materials to the kinds of applications. What do we have to do to design better materials? What do we have to do to design better devices? And that's where a lot of the science and engineering goes on. And these are some examples of the sorts of applications. So making electroluminescent devices for displays and lighting. And this is an organic light-emitting diode angle poise lamp. You can see here. There's also an organic light-emitting diode display in the back of this camera, which you won't be able to see from where you are, but if you'd like to come and have a look at it later, please do so. So displays and lighting. There's a large amount of work being done on field effect transistors. There's increasing amounts of work on solar cells and photodetectors. People are also interested in thinking about optical communications, imaging and analysis systems. So these are some examples of the sorts of device structures that you can make. Within this talk, I'm going to focus, in terms of further applications, on photodetectors and a little bit relating to optical communications and microanalysis. What we're trying to do is to make use of flexible properties, the integrability of our materials, and their versatility to come up with a whole range of different applications. And those are just some of the applications that people are trying to look at. And it is this opportunity to do things in different ways that is really starting to attract quite a lot of interest. And so I'm going to come back to my humble fan, and I'm going to turn my humble fan on. And what you can see is it's not quite such a humble fan. It actually has light-emitting diodes integrated into the plastic vanes of the fan. So that's just one example, a very corny example, but nevertheless it gives you some idea of the sort of changes you can think of making when you have this combination of new materials, flexible materials with plastic processing. So moving on, I'd like to say a little bit about a discovery and some first applications. So a little bit of history here, but also I think trying to, if you like, point out something about how this field has developed. And if we cast our mind back to the sort of late 1980s, up until that point, the majority of work was looking at materials that had high conductivity. People talked about synthetic metals, and also materials that were of interest for nonlinear optics. And these are two examples. This is transpolyacetylene, and this is a polydiacetylene. Now, the conductivity attracted a lot of interest, and in fact was rewarded with the Nobel Prize for Chemistry in 2000 to Alan Higa, Alan McDermott, and Hideki Shirakawa. But in the end, these materials are not very good metals. The conductivities can be quite high, but it's very hard to make them stable, to make them into useful functionality. And so this area was starting to wane in terms of its interest. Similarly, in terms of nonlinear optics, these polydiacetylenes, and in fact, this was one of the material systems that my father worked on. He was interested in nonlinear optical properties of these materials. Nonlinear optics, people were interested in making optical switches, all sorts of optical devices for optical communications. And in the end, very little came out of it. In fact, the biggest success in terms of using conjugated polymers in terms of optical communications was to make thermal switches. And thermal switches are extremely slow. And in fact, it doesn't actually matter which polymer you use. They all basically give more or less the same thermal response. So after a huge amount of effort, essentially this field was coming towards a close in terms of its potential for application. And so this waning interest, notice also these materials are very weak light emitters because of the nature of their excited states. If you like, this field was kind of starting to run out of steam. So what changed the interest in this field? Well, what changed the interest in this field was basically people started to look at different sorts of materials, and these are some examples of the kinds of materials, and also to look at different properties. And in particular, a lot of interest was generated by a serendipitous discovery in the Cavendish laboratory, which showed that it was possible to make a light-emitting diode out of conjugated polymers. Now, this is a schematic of the device, and the first thing to say is if you look at that, it obviously is not designed to be a light-emitting diode. And it wasn't designed to be a light-emitting diode. It was actually a test sample that was being used to test the dielectric breakdown strength of this layer. And the reason we wanted to know what the dielectric breakdown strength of that layer was that my colleague Jeremy Burrows was working on field effect transistors, and he wanted to make plastic field effect transistors and wanted a plastic insulator that could be used to provide the dielectric in that structure so that you could apply a gate voltage to the structure and produce a field effect transistor. And I had previously worked on this particular polymer, this PPV polymer, and knew something about it, and we basically decided that it would be an interesting material to test as a dielectric for use in those field effect transistors. And so very simple structure was made, essentially aluminium on both sides. One side has a thin layer of oxide because it was exposed to air in the preparation of the device structure. And the idea was simply to crank up the voltage and see when this thing failed. And that would be your dielectric breakdown strength. Now, there are obviously much more scientific ways of working that out. If you do dielectric spectroscopy and all sorts of other things, this is the quickest way to find your answer. So that was actually the experiment that was done. And if you apply a bias to this structure, this is some of the original data, basically you increase the voltage, you get to 25 volts, and then suddenly you start to see a current flowing through that device. And it's not a breakdown. It's actually, there is an injection of charge into the structure at that point, and you get correspondingly some luminance coming out of the device, not very much luminance, but there is some light emission coming out of that structure. And so this structure is actually an organic light-emitting diode. Wasn't designed to be, is certainly not the best device structure to achieve that. And if you work out, was this a good dielectric? It was actually, because it's 3 megavolts per centimeter is the point at which this voltage actually starts to inject charges. So if it hadn't been a good sample in terms of its dielectric properties, it would not have been possible to inject charge into that structure. We see a nice linear luminance currents relationship, and the emission spectrum is characteristic of the polymer, so we can show that it's electroluminescence. The efficiency of these devices, 0.01% photons per electron. That's not a lot of photons per electron. It certainly wouldn't excite you in terms of making a device. The good thing at that time was the target was about 1%. So there were no gallium nitride LEDs at that time. There were no quantum well LEDs being used as they are today. So essentially the competition was not very great, and therefore this actually looked quite interesting. If it had been discovered today, people would probably have just thrown it away. You know, you would look at that and say, well, there's no point if we look at what else is available. So sometimes timing is quite important. Some of the things we knew was that there was the opportunity for color tunability through chemistry. We did a very simple experiment to measure the frequency response. So this is electroluminescent signal as a function of frequency. We basically found that we had a fast enough response to think about doing video displays. And this solution processability offered the prospect of all of the things that we think about in terms of plastic substrates, flexible deposition, and so on. So low cost, high throughput. And basically, this is a patentable invention. Now, again, at that time, it wasn't actually very common to patent things. And in fact, when we first went to the university exploitation office and said we wanted to patent something, the first question they asked us was why. And we explained why, and they said, OK, fine, go ahead. And we then asked them, did they have any money to help us patent it? And the answer was no. So it really wasn't a time when people were trying to do this sort of development work. Nevertheless, we did decide that we would do it. And so myself, Richard Friend, and Jeremy Burrows sat down to write a patent. And we'd never written a patent before. And we basically had to write it just thinking, what do we think might be the important things to put into this patent? And we went ahead and did that. Thankfully, it turned out to be quite a good patent, so it actually stood up to a challenge from Philips, no less, a few years later. So it was actually quite a fortuitously well-written patent. It was also probably the most general patent I am ever likely to be able to write, and probably the most general patent that most people would ever be able to write, in that essentially claim 1 was an organic light-emitting diode comprising a conjugated polymer. And it doesn't get more general than that. And that was actually then what enabled this to go forward, and many things came subsequently out of that. So here's some early days photographs. Here's a nice picture of our integrated, compact, low-cost light-emitting diode in a vacuum chamber with a magnifying glass, so you can actually see there is some light coming out of this structure. And though this is not one of the very earliest, this is a few years later, after the original, or a year or so later after the original discovery. We now are measuring proper units, so we're measuring luminance in candelas per meter squared. And if you look at these numbers, 10 to the minus 1, 1. If I tell you that a computer display is 400 candelas per meter squared, there's clearly quite a long way to go from this sort of performance to something that is useful. But our target was 1%, and that was reached in 1992. So a paper was published in Applied Physics Letters reporting that. And at that point, it was decided to start a company, and Cambridge Display Technology was founded by myself, Jeremy Burrows, Richard Friend, Andrew Holmes, Paul Byrne, and Arno Kraft. And that was the start of this particular company. So you'd forgotten, I suspect, about my link. Well, here's one of the links in the story. So here are the 3 gentlemen that we showed on that slide. And I note sartorial color gamut, red, green, and blue. Note also partial attempt at contrast enhancement. They're standing against the black screen. So they obviously were very much into this idea of making displays. They were actually early investors in CDT, known as Genesis, in this context known as Hit and Run Limited. Now, if you go to a venture capital company called Hit and Run Limited, it doesn't necessarily inspire you. But they were actually one of the groups of people who decided that this did look interesting and that they thought it would be worth investing in. So hopefully they made something out of it. But it was very nice to sort of see people like this looking at technology and saying, we should be supporting these kinds of activities. So what do you do if you have a very poor device? How do you try and turn it into something that is going to be useful? Well, you can do a lot of things. One thing is basically to look at the device physics and to look at engineering. And you can look at the processes that are involved. So exciton formation process, break that down into a number of steps: injection, transport, carrier combination. The decay of the excited state. You can look at extracting light from the structures. You can look at making them more stable. And these are all the things that you basically have to do. And a lot of work has been done over the years by a great many people to address all of those sorts of issues. Now, this obviously also goes hand in hand with materials development, not just the emissive layer that you're using, so not just the plastic electronics component, but also all of the other materials that you need in terms of electrodes, optical control layers, and encapsulation layers. This just illustrates the sorts of things that were done in terms of chemistry, and it really is a triumph in terms of the chemistry to bring these materials through to real applications. You can do a whole lot in terms of designing different sorts of chromophores. You can introduce heteroatoms into these structures. People started looking at blends in order to optimize properties. Problem with blends, as any polymer physicist will know, is that they tend to phase separate, and controlling that phase separation is quite difficult. So people then went on to make complex copolymers, where essentially you would add together a whole series of these different units in complex ways to end up with a material that provided the different functionalities that you wanted. And you can widely tune properties like the optical properties, but also energy levels and the details of the spectral characteristics. Things moved on. This is a device in 2000, and if you look at these numbers now, we're talking about 1,000 and 10,000 candelas per meter squared, so not 0.1 and 1. So things have moved on quite a lot. And here is the first commercial device from Philips. It's a shaver, so it's called the Spectra Shader, and it has an organic light-emitting display in it, which is similar to the sort of display that's in this box. Let me just switch that on. So this was the first product. Here's another product from similar sort of time from Osram. So these are passive matrix displays. Now, you might think that a shaver is not a very exciting product. But I have to tell you, Philips were extremely excited by this product. And how do I know that? Well, I know that because of this. Okay, so we're back on to our slides. So, Die Another Day. I'm sure you all remember the film. This shaver was sold as James Bond's shaver of choice. And if you watch this film, I don't know how many people's memories are that good if you've seen it, but there is a scene in which James Bond swims across Hong Kong Harbour in a rather disheveled state. In fact, he looks rather like Robinson Crusoe, I have to admit. And he turns up in a very posh Hong Kong hotel and checks into his presidential suite. And when he checks into his presidential suite, he's given the finest champagne, so Bollinger on ice. He's given a whole set of new shirts and tailored suits. I don't remember. I think it was Armani, but never mind. And he's also given a Philips razor. And in fact, there is a good couple of minutes in this film in which you see him shaving with the Philips razor. And if you look carefully on the side, there's a little presentation box which says quite clearly, Philly Shave, if you look carefully. So it's all there. It was advertised in that way. It was put into, this must have cost a significant amount. And it clearly shows that Philips were very excited by this product if they decided to actually go ahead and do this. Now, the one thing that puzzles me about this Philly Shave razor is I can understand how he got rid of the beard, but when he went into the hotel, he also had very long, straggly hair. And by the time he was up in his room, it was nicely coiffed. So I'm not quite sure how this particular razor does all of that. Maybe it's a continuity issue, but you should have a look and see. So color, we can basically use the chemistry. So this is an example of using chemistry. We can basically arrange to have the three colors. This is a way of representing those colors in a two-dimensional plot, which is called a CIE color coordinate chart. And basically on this color coordinate chart, we can define a green point, a blue point, and a red point. And this particular triangle is defined by the European Broadcast Union as the ideal color representation if we want to make a very nice display. Now, one of the things I told you earlier, and in fact is illustrated here, is that these materials emit rather broad bandwidths, so up to 100 nanometer bandwidth. So how do we get, so this particular line here is basically the line that defines saturated colors. So how, for instance, do we get colors that are very close to being saturated using these broad band emitters? It turns out that probably the main reason is that the photodetector that's relevant to displays is the eye. And it just so happens that the pigments in the eye that detect the photons are molecular materials, and they're actually conjugated molecular materials. And so they are actually rather well matched spectroscopically. The absorption spectrum of those materials and the emission spectrum of these materials are quite nicely matched. So you get, in fact, very nice bright colors using these broadband emitters. And we can basically use a range of different chemistries to get a whole series of materials, and then you can basically mix those materials to get a nice white, and you can use that white, for instance, to make a light like this one. We talked about processing. This is just demonstrating that processing is possible. 2 examples. This is from CDT. This is from Epson. These are inkjet printed light-emitting displays. And if you remember where we were at the beginning, in 2003, people were already making fully inkjet printed displays, color displays. Epson made a 40-inch prototype in 2004. So it really is amazing once engineering comes into play how rapidly the technology can advance into these sort of display progress. So what have we been doing in recent years? We've been looking at a number of other elements within this device structure. So looking at the electrodes, looking at injection layers, looking at these transport and emission layers, and in particular trying to do things that, if you like, take these materials into new spaces. So looking at making them on a flexible substrate. These are actually printed using a gravure printer, so the kind of printing that would be done to make a newspaper or a magazine. We can basically make devices that have no indium tin oxide, which is a difficult material to use on a flexible substrate. We're looking at ways of getting rid of some of the reactive metals that are typically used to inject electrons, so these inverted structures on a flexible substrate or on a glass substrate, and then also looking at novel ways of patterning in order to make pixelated displays. And so there's a whole range of activity that is ongoing in terms of the display research, which hopefully will then translate into display products. So moving on, developing additional applications. Just briefly talk about some other applications that people are now starting to look at. The first one is lighting. And again, you can really see that you have the opportunity to do lighting in a very different way. Now, this looks like an angle poised lamp. It's very thin, for one thing. It's also very cool, so it doesn't burn you if you basically touch the element. It's also very efficient, so it has attractions from that point of view. You can think about making very unusual lamps. So this is a sort of a strip which is all curled up to make an interesting lamp. You can think about making wallpaper that emits light. You can think about making flexible shaped devices. You can think about basically making light-emitting strips for clothing. There are lots of things that you can now start to do. So panels, lamps, wallpaper, blinds and curtains, window panes, workspace screens, clothing. People are also now thinking about doing photodynamic therapy using stick-on light-emitting diodes so that you can basically walk around whilst the treatment is being given. So these are just some of the examples of opportunities to use these materials in lighting. We're also looking at using these materials to make photodetectors, and we have been working with a company called Molecular Vision to develop a new range of instrumented lab-on-a-chip devices, so microfluidic structures where we have a light source and a photodetector. And this allows us to basically make point-of-care functional devices that have a quantitative output. So the output is basically as good as you can get when you send your sample off to a laboratory, but we get it in real time locally. This just illustrates the device structure with a light source and a photodetector. We have our microfluidic channel where we do the chemistry. We can then detect the results of that chemistry. This shows the response of one of these photodetectors, a very nice linear response over many orders of magnitude that allows us to give very good sensitivity. And there have been good developments in terms of the company. So this is a manufacturable prototype from a couple of years ago, just illustrating that you can make a structure which is handheld, portable, gives a quantitative result using quite simple components and combining those components with organic light sources and photodetectors. Third example is optical gain media. So this, again, is a light emission example, but it's basically using these materials to provide stimulated emission. And we basically find that we have these materials that we've already been talking about have quite high optical gains, about 50 per centimeter, and these large bandwidths. And we can basically tune the materials to cover the full visible spectrum, and we can use those to make quite simple lasers. So these are one-dimensional lasers, so we get a stripe laser output, or we can use a circular grating to make a two-dimensional confinement to give a nice focusable output, as shown here. And these devices we can pump with relatively low energy, so picojoules to nanojoules, a few hertz, few nanosecond pulses. And we're interested in then looking at applying those in a range of applications, particularly data communication applications would be one, but also probably in a number of other areas as well. And the kinds of things we're looking at, fundamental laser and photophysics, and their applications to sensing and metrology. We're looking at functional components that would complement the now very widely used polymer optical fiber. So polymer optical fiber is finding a wide range of applications in the automotive sector, for instance, for moving data around inside cars. We're also interested in a range of hybrid structures, so combining our organic materials with more traditional inorganic semiconductors, and also now with structured metals, what we call plasmonic materials, and then also trying to move towards electrically pumped structures, which still remains a big challenge for our material systems. So finally, talking about some examples of, if you like, more focused research, we're looking at opportunities to use the molecular properties of these materials to do things in different ways. And so one of the areas we've been looking at is basically inspired by research that's being done on material systems that are called metamaterials. And I'm very pleased to see that John Pendry is in the audience this evening. Metamaterials are materials where we basically physically structure the material on a scale which is short compared with the wavelength of the radiation, the wavelength of the light that we want to interact with that material. And by doing that, we then have an averaging of the response of the material associated with that structuring. And in particular, you can make structures which show unusual properties. And some of the unusual properties are perfect lenses, and we can make negative refractive index materials. And those are typically made using metals, which are structured. And there are a whole range of different geometries that are used to achieve that effect. What we've thought about is to look at trying to obtain some of these effects in the visible part of the spectrum, where essentially we now need to be able to structure our materials physically on length scales which are short compared to the visible light, so very small length scales, so in the tens of nanometers or less. And basically to think about trying to do that with molecules, and in particular, trying to do it with molecular conformation. So we're coming back to something we talked about earlier in the talk. So the ability to change the conformation of our polymer, if that conformation change also induces a change in the interaction with the optical field, and if we can basically spatially pattern that conformation, then we have the opportunity to make some interesting materials in this area. And in particular, we're looking at using this beta phase of dioctyl fluorine. So this is an extended chain structure. This is the beta phase structure. This is sort of the more typical, if you like, exploring three-dimensional space structure for the polymer chain. If we arrange that we have this elongated segment, then what we see optically, so this is absorption, is the appearance of a new absorption feature. And this absorption corresponds to having a fraction of segments of polymer chain in this conformation. And it's that same conformation which gave rise to the gelation that we talked about earlier on. And if we look at the luminescent output, we can quite clearly see the contrast. So this is a sort of turquoisey color. In this case, we have a typical blue color. So the question is, can we spatially structure that? And the answer is yes. And this is just one example of doing spatial structuring, where we've used an exposure, a masked exposure to a solvent to generate this conformation. And so this is a cross-section through a stripe where we've generated the beta phase conformation in a sample. This is looking at two different wavelengths, so we can see that the refractive index variation changes with wavelength. Basically, we end up, in this case, with a refractive index contrast of about 1.4%, which is quite similar to the sorts of refractive index contrasts that are found in typical silica fibers. We have a nice graded profile here, which is quite good if we're thinking about making guiding devices. We've also looked at making some active structures. So we've now, you can quite clearly see the beta phase with this turquoise emission, the more typical glassy phase with the deeper blue emission. What we've actually done is to do this patterning on top of a grating. So underneath this film, there is a grating. And that grating provides a feedback which makes this structure a laser. And then simply by spatially selecting the point at which we excite the laser, we can basically modulate the output wavelength from that laser corresponding to the amount of index contrast that we generate. One of the very nice things about these sorts of structures is that they're planar structures. We don't have to do any lithographic patterning or any electron beam writing or anything like that to generate the structures. There are no changes in the threshold or slope efficiency, so the patterning process is not doing any damage. And so it's actually very easy to think about making a range of structures where we could make use of this effect. And this is one of the areas that we've got work going on. I think I'm running out of time, so I'm just going to skip a few of these slides. I thought I would, but I'm always optimistic in terms of, oops. So in conclusion, I hope I've been able to illustrate to you how we can think about molecular semiconductors, molecular electronic materials in terms of their basic properties, and then try and link those to a wide range of applications and look at how it's possible then to make interesting and different sorts of devices. And finally, there is actually one of these that we didn't talk about, and that's Wimbledon College. In fact, John had half the answer earlier on, so I did say, have I got news for you, was part of the story. Have I got news for you? One of the presenters is Paul Merton, but Paul Merton is not actually Paul Merton, he's Paul Martin. And Paul Martin went to an institution called Wimbledon College, which is in the London Borough of Merton. Now, that's not the only connection. For those of you who are eagle-eyed and have good imagination, this is actually me. So I'm also somebody who went to Wimbledon College. This was in the days when I still played rugby, and that's what that photograph is. So that's where I would like to stop. Thank you very much for your attention.
Thank you very much. We have time for a few questions, and there are roving microphones. So two things. If you could, first of all, wait till a microphone comes to you, and secondly, if you could stand up when you ask your question so that you can be recorded. So.
Hi. Will Stewart. It's a brilliant lecture. Thank you very much. Donal, I was wondering, the wavelength range, you've talked very much about the visible. Can you comment on whether this could be pushed out, for example, into the infrared a bit further?
Yes. So, I mean, the easy bit is to do the visible. So there are materials that will go further into the infrared, but they are less well developed. People are quite worried about some issues in terms of their stability. But the kinds of things that you could think of using are things like phthalocyanines. Some of those will emit into the near infrared. There are dithiolines also. People are interested in looking at some of those materials. Squareanes. So there are a range of materials that could be developed. Typically, they're not particularly emissive materials, but I think it's probably also the case that not that much work has been done to address that particular wavelength range, and so I think there is an opportunity to do more in that area.
Other questions? At the front there, and then afterwards.
Hello there, Andy Delaney. I've got a question for you. One of your slides had an image of a man sitting by what seemed to be a painting of a tree on the wall.
Yes.
And I wondered what applications are relevant to art and maybe sculpture or painting for this technology.
So the picture was actually light-emitting wallpaper. We go back. So it's this one. So this is a designer, Jonas Salmon, And this was his idea of one of the ways in which you could use this sort of technology in a different sort of way. And so what he's done is to make, this is a piece of wallpaper. Wallpaper may be in inverted commas there, but it's basically an installation on a wall where he essentially has designed this tree-like structure to be a light-emitting object. And so you could think about designing your own, you could have this custom-made for your own space, and you could have all sorts of different structures. You could basically think of having different colors. People are interested in what they call mood lighting, so ability to basically tune the colors to a particular time of day or your mood or whatever. So there are, in fact, very interesting ways of thinking of using this kind of technology in an art-related way. And it's just, the opportunity is there. And I'm sure there will be a lot of development in those sorts of directions.
Thank you. I'm Alan Sturt, and I'd like to ask you what sort of lifetime these materials have, because all polymers degrade, and you can envisage a time when all those lights go out.
Yes, no, that's obviously a very good question. And I think initially people were extremely worried about the lifetime of these materials because, as you say, it's well known that a lot of these materials suffer from a variety of degradation mechanisms. I mean, what's interesting is that the original LEDs that we made, the failure mechanism was actually losing the aluminium from the polymer. And if we strip that aluminium off with sodium hydroxide and put more aluminium on top of it, it would light up again. So that gives you some idea that not all organic materials are weak in that context. Now, typically for the display applications, they are encapsulated. So the device's structures are encapsulated. And that is basically, or principally, to protect the electrode, in particular the cathode, which is used for injecting electrons, from moisture. So typically those cathodes are made from reactive metals, so lithium, barium, calcium, those sorts of metals, and they obviously degrade very fast. If you do that encapsulation, then people have been able to make display devices where the light-emitting diodes have lifetimes in the 300,000, 400,000, 500,000 hours range. So under normal use conditions, 5 years, 10 years type of lifetimes. So the lifetimes are not actually that bad. I mean, there's still plenty of work to be done, and people are still doing a lot of work to address that particular issue. But it is possible to do that. One area I didn't talk about was solar cells, and this is an example of a solar cell. So again, making use of the properties of the plastic materials to embed it in the side of a bag. This is a much newer area, and people are really only starting to explore that in detail now. The company that made that particular solar cell is Kanaka. They have had roof panels on a roof for a period of 2, probably going on for 3 years now. And in fact, over the first year to 2 years, they said they actually improved in performance. I have no idea why that would be the case, but they didn't actually degrade in terms of their performance over that time. So I think if you put organic materials in the right environment, and that right environment depends on lots of factors, then they need not be unrobust. They can actually be quite robust in many respects. Another thing that is worth noting is that if I drop my laptop computer, the biggest problem is that the screen cracks. And the screen cracks because it's basically on a piece of glass. If I put it on a piece of plastic, it probably wouldn't crack. So again, there may be ways of making products that actually turn out to be more robust because of the features of the materials that we're working with. And so we're looking on the positive, but your question is is a very important one. But it does turn out that the stability is much better than certainly we originally imagined it would be.
Thank you, Donal. I think I should say at this point, this is quite a remarkable story that's been described in a space of some 20-odd years, I think, from what was originally, as you say, a serendipitous but essentially basic science discovery through to the extraordinary range of technology which you've just demonstrated for us today. It's quite a remarkable combination of that basic work and also the applications out into everything, out to economic benefit. It's also very nice also to have the entertaining aspects of this, and I wasn't certainly aware of all those wrinkles and connections, so if there's a budding Paul Merton out there, I'm sure we can do that. So we have, I think, a token of appreciation and some records, here they are, which I should formally hand to you now. And I think on that note, I think we should express our appreciation for this remarkable Bakerian lecture by Donal.
Thank you very much.